So welcome everyone to our monthly ICG Lab Talk series. So here on the Zoom call, we have only people from the Institute, but the talk will be streamed live on YouTube, and we will also make a recording available via YouTube, if that's okay for Michael. And I will keep an eye on the YouTube chat, so feel free to post your questions there, but you can also send emails, and I will also keep an eye on that. So without further ado, I'm happy to introduce Professor Michael Sedlmair to you. Michael did his PhD with BMW, supervised at University of Munich, and then did a postdoc at UBC and University of Vienna. And he's now a junior professor at the University of Stuttgart, and his interests focus on InfoVis, interactive machine learning, virtual and augmented reality. And I guess it's safe to say that Michael is one of the young superstars in our field. So it's really great to have you here. And now Michael is going to tell us more about the love story between machine learning and visualization. Michael, you can take it from here.
Okay, thank you very much for this lovely introduction. So the bar is high. I think of myself just as a normal researcher, so no worries here. Okay, so let's talk about a little bit about the love story between machine learning and visualization. It's not probably always love, but I think there should be some love involved between those two fields. I thought about starting like approximately 15 years ago when I personally started my journey into research in this area. So I still remember that I was really fascinated by data. Data became available everywhere, and back then I mostly was interested in HCI. So I did my studies in media informatics and did a lot of things in human computer interaction. And so for me, a logical thing to combine those two was, I think for most people it would have been the same, to do some visualization. So visualization is the lens for humans to look at data. And this is pretty cool. So this is also when I dived into my PhD at BMW, as Mark already said, and building some cool visualization tools. At least we thought they were cool, and transported data from the computer into people's brain and let them interact with the data, but also in other areas. So after that, some 10 years ago, I think also it officially became clear that data will change the world. So we probably all do remember the book of the fourth paradigm of science. So data is the new oil. Data is the way how we will better understand society, the sciences, industry, and basically all parts of life. And so this is when I started my postdoc at UBC in Canada. And when I moved there, for me, the worldview was rather clear. So there's visualization with humans and data, and then there's the machine learning world, which I found really, really interesting, which is more the algorithmic world, so without a human in the loop. So there were people like, Kevin Murphy at UBC, Kevin Leighton Brown, Nando de Freitas working in machine learning back then. I was really fascinated by that area. There was also NIPS, now NeurIPS in Vancouver. Back then, this was a Vis-sized conference, so with say 1,000 people or so. So on par. But then we all know what happened. So here, this is my feeling of what happened over the last decade. Machine learning has gotten super big. So we know there's data science. There was big data, all these trends, AI. And people have really thought about automizing everything with machine learning. And there's this really interesting epistemological difference between machine learning, where you you want to automate basically everything. You don't want to have a human in the loop, and visualization, where we always think about human in the loop. But machine learning, became much bigger. And I was like, hey, this is sort of crazy. By the way, this is not intended that this is a corona looking like virus graphic here. That's just on purpose. The thing is all of a sudden machine learning became the center of also many other research areas, and everything sort of in my worldview centered about this let's automatize everything. While I still was wondering, hey, essentially, we need a human in the loop. So the HCI people, they're always like, let's do things for people and let's not replace people in this process. And so this is in some ways what I think of the future. I feel like, the human will become more important again. But we need a combination. We need to think about how to combine these fields of machine learning and visualization. Also, of course, like, any other field that deals with data. But I think those two are really essential. So this is something that I have thought about for the last decade quite a bit. So how can the two fields of machine learning and visualization benefit from each other? And also, how can we combine them? And I thought, like, this might be also knowing what Mark is working on, for instance, might be an interesting topic for this crowd today. So there will be three parts based on that. So we will start first talking about visualization for machine learning. So I try to use the color blue for visualization and red, like this will be machine learning, as you already noticed. And then in part two, we will switch gears and talk about what machine learning can actually do for visualization, design, and research. And then in the final part, I would like to talk mostly about challenges, but like the holy grail in some ways is putting both together. So not one for the other, but both together, visualization and machine learning. So how should we or could we combine them, and what is the value for us? Okay, so let's dive into the first part, visualization for machine learning. Okay, so probably all of you have seen some sort of like evidence that visualization can be really useful for machine learning engineers and machine learning researchers. Interestingly, I think the first papers that really made this clear came not from the Vis community, maybe like, because machine learning had already been too big, so nobody was paying attention to our work anymore. But I think like one of the first like really influential paper that I think of was like this paper where they explained how neural networks for computer vision, so for like, how computers see images in the real world works, and how visualization can be used to actually reveal how each of these levels show how the computer would actually perceive a real world image. But there's also many, many other examples. And I think by now you could like, list hundreds of examples here, like easy ones like explaining gradient descent, like, or even here, like, explaining TensorFlow. There's this TensorFlow playground tool that you probably have seen. It's very nice. If not, please take a look. I think those are interesting and nice tools. So we also have been doing work in the area for the last decade on how we can use visualization for understanding machine learning models. But I think our focus has been somewhat different. So most of the work that I've seen is really focusing on like understanding a specific model instance and like, trying to open this black box. So looking into how like a deep neural network, for instance, works. So we always have been more like on the front of like trying to understand ensembles of models. And so a very typical task here would be just to like do model selection. So select a good machine learning model among many models that you train. I want to like use a concrete example to do that with my favorite type of machine learning models, if you want. So, and this is like, just dimensionality reduction algorithms, which is often used in the pipeline of machine learning models. So probably all of you know that, but like let's just briefly recall what a dimensionality reduction algorithm is. So we have some high dimensional data or multi-dimensional data about cars. Of course, I'm using cars because I'm in Stuttgart now. And then like, they have like, multiple dimensions. And then we can use one of these dimensionality reduction algorithms, PCA, MDS, TSNE, UMAP, ISOMAP, you name them, your favorite one. And then you project them usually down to 2 dimensions if you want to do visualization, because then we can just plot them into a scatter plot, and we can do things like looking for clusters or also interpreting the new dimensions that we get here. So the tricky thing now is, what is the right algorithm that you want to use? And what is the parameterization you want to use for those algorithms? So, and this is not just a purely hypothetical problem that I'm coming up here. So we did a field study a while ago when I was in Canada, and we interviewed people on how they use dimensionality reduction algorithms. And I think the most typical problem really was like, what's the what's the best dimensionality reduction algorithm and parameterization for my problem? So how would people like in the wild go about that problem? So they pick their favorite one, PCA, then they look at the data and they're like, sort of unhappy. I don't see the patterns that I expected. So then they use another one, and this is now a parametric one, like use TSNE, for instance, with a new, with a first parameter setting. They're like even more unhappy. They try a different parameter setting, and they do an approach that we call like, trial and error. So you're just like, unsystematically going through the space, or like, with some sort of like, systematic, but there's lots of problem. You can't recall what you did in the beginning, like you don't know what exactly to do next. And like, at some point, this can be a very frustrating process. So the idea here instead is to do a systematic visual parameter space analysis. This is what we call that process. So instead of like, doing that sequentially, we sample an ensemble of algorithms of dimensionality reduction, projections in that case. And then we have a visual interface that we can show to people. And you see this little guy here or girl already smiles a little bit. And if we now like, do a really good visual representation, people can do this analysis and the selection process in a more systematic, more satisfying way. This is the idea. A core component, we built many of those systems that we found here is what we call a meta map. So like you get an output from all of these algorithms. In that case, that would be a scatter plot. So we can now take each scatter plot and put that into like the dimensionality reduced version, or like, a MDS plot or whatever, again, where we basically encode like the similarity in the distance. Okay. So like if I have something like this is over here, that means these scatter plots, these projections would be similar. So this is a core idea that we're often using. Okay, so let me try to illustrate that with like a more concrete example here. So this is the Vis Coder tool that we built together with my PhD student, René Chutura, who's, by the way, still sitting in Vienna. So the idea is really to have this visual interface that allows you to support people in selecting but also analyzing ensembles of different dimensionality reduction models here. Okay, so this is the tool. In the center, we see this view, which we call the meta map. So each dot that you see here is basically a dimensionality reduced version of the same data set. And we use some like, colors to encode the different types. So you see we had like a TSNE here, isomap, MDS, PCA, also an LLE. We will today only focus on TSNE, which has two parameters. So there's the perplexity and the epsilon, which we encode in this two-dimensional color ramp here. Okay, so we now can look at the video here. So if we now click at these, this is the typical details on demand. So we see this is actually a projection. And now we do our favorite interaction technique. We do some linking and brushing. And now we do that with a bounding box here. So we draw a box around like certain projections here in this meta map. And so we remember if these projections are closed, they mean they're similar in the way they appear to the human viewer. And interestingly, if we now look here to the left, we see that there's some interesting phenomena happening in terms of the two parameters that we're having. The perplexity seems to be really similar also for these values, while the epsilon is all over the place. And now we can follow that. This is actually the case all over the place for these, like, 1,000 TSNE projections, or roughly 1,000 that we generated here. We also can do it the other way around. So we now select all the scatter plots that are all the projections, that have the same perplexity values, and we see they're close to each other. And we can actually do that over the entire space. However, if we now do the same thing with the epsilon, we see that there is, they're all over the place. Okay, so what does this mean? Okay, basically what we did here is a sensitivity analysis. So we saw that, like, the TSNE projections, they're like their sensitivity in terms of the perplexity parameter is what we expect. So like, things, projections change if we do change the perplexity. If we change the epsilon, like, there's no visible effect. That either means like, it's super sensitive towards that parameter, or it's not sensitive at all. So we learned something that can help us to identify some good dimensionality reduction methods for our purpose. Okay, so visual parameter space analysis is a general model agnostic framework to analyze input-output models. Okay, this is a very generic definition here, but the point is this is not just useful for machine learning models. In fact, we saw using that for classical simulation models where you know how like the models work instead of like, just training them from data. So we did that, for instance, for image segmentation or bird simulations, as you see here. And also many other people use that approach. So here, for instance, there's the flood simulation by Vasa et al. From Vis in Vienna. There's also like, simulations of how you would design an insertion needle for operation. So this works really well. So what we did in the last 10 years is really looking how we can use that approach for machine learning models. So I showed you that we can use it for dimensionality reduction, but you can also use it for many, many other machine learning models because most of them are essentially also input-output models. We can sample them. So we use them for clustering. In fact, this was the first thing that we did some 8, 9 years ago. We also used them for classification models. We published that, in fact, at AVI last year. Okay, so this is not updated yet. We also use that for active learning. So this is a very generic approach that at least I personally made really good experiences with. If you work with experts that seek to better understand the space of possibilities that they can use their algorithms for. Okay, so this was part one. Visualization for machine learning. Let's now switch to the second part, machine learning for visualization. So here is our corona virus looking like overview graph again. So a few years ago, like 3 or 4 years ago, I really was wondering. So people started really thinking about the combination of machine learning and Vis. There was like workshops at the IEEE Vis conference. There were also tutorials and other things like panels. But most of them really talked about like, how visualization can help machine learning. So the things that we talked in the first part of the talk. However, if I look to other areas, then I think like all the other areas, they just thought about like, what can we, like our area, take from machine learning as a new method? And visualization seemed not to have done that so far. This is very unselfish, right? These people want to help other people, like the poor machine learning researchers. This is very nice, but at the same time, I was wondering, there is probably also something that visualization can take for machine learning and use it to improve our research and our the work of the designers and the tools that we're building for them. So and this is the second thing that we did, and like to illustrate it, I want to use an example here that illustrates one of the grand challenges, I'd say, in the area of visualization, which is like designing good visualizations. So here I'm using this example, and I think, Mark, please correct me if I'm wrong, but I think I originally saw that first in one of your presentation, and you said it's originally from Niels Gellenborg. So if not, then it's from somebody else. But I think it's a very good illustration of like what we're talking about here. So we have some data, super easy data, and now we want to visually encode that. And now, of course, like, if there was no corona, I would ask this question into the round, how would you do that? And everyone would, of course, say, like, we're going to Excel and just let do Excel the job for us. And then, like, Excel suggests a 3D bar chart, and we can, excuse me, obviously see the pattern in this data, which is some small bars and some long bars. But like, then we might be unsatisfied, and we might instead pick a heat map visualization where we use color for visualizing this data. And of course, we immediately see this interesting pattern of a question mark here. Mark, is this an example from you?
I think Niels published it in Nature Methods at one point in time.
So it's an important example, as you see, because it's from Nature Methods. Okay, great. Okay, so the idea is clear. We need to find good visual encodings that help us to pick good to pick good visual encodings that reveal the patterns in the data, or even like, more simply, to make people more efficient in the tasks that they're doing. I think this is a core thing that many visualization designers and also visualization researchers are working on. Okay, so how do we do that traditionally? Traditionally, we would talk to the HCI-ish flavored people in the Vis community and say, we need to do some user studies. Okay, so here's one of my favorite ones. It's also an old one from Goniam and also Jean-Daniel Fekete, where they compared, for instance, matrix visualization, adjacency matrix visualizations to node link diagrammed visualizations of some graph structures here. And so they found out that usually actually the node link diagram really sucks, apart from path tracing tasks. And the adjacency node link diagram is much better for all the other tasks. By the way, we remember what happened in the meantime, people still heavily using node link diagrams. So there's probably not the final answer. Anyways, so this is really cool because it gives guidelines to designers. In that case, they read the paper and then they can say, oh, I probably should use adjacency matrices instead of a node link diagram for my purpose. However, the drawback is that this is not something we can formally specify into an algorithm. So we still need a human designer or a human expert to read these papers and to know about these guidelines so they can actually be used. So some 10 years ago, there was this really interesting idea, which stems from classical data mining research, which is, hey, can't we just define some measures or some metrics that do exactly that job for us automatically? And so the idea is essentially that there's an algorithm here I illustrated with this R2D2 robot that does the job of the human. So this robot looks at the visualization and knows what is good, what is interesting. And so the first series of measures that I saw, I like to call them heuristic-based measures. So they're just saying, okay, something is going on, and we can take that as a means of measuring how interesting something is for human observers. So let's assume we want to measure, for instance, class separability. So the assumption here is scatter plots that have more separable classes are more interesting ones than compared to the ones that just bump everything together into a one cluster. And so here you could, for instance, use the centroid measure that was proposed by Mike Sips in 2009. So you compute a centroid for each of these classes, you iterate over all the points, and then for each point you essentially just measure, is this point closest to my own centroid, in this case the blue centroid, or to some other centroid. If it's closest to your own centroid, the value goes up, or in this case the red point is closest to the blue centroid, the value of the metric goes down. And so then you do that for all the points, and you get actually a measure that you can use to automatically and say how separable these classes are, i.e. how interesting is this view for a human observer. So far, so great. So what we can do then is we can just select good views, for instance, in a scatter plot matrix. So the main limitation of this approach, this is a really nice idea, but we found that it's really not generalizable across many data sets. So why do I say that? So we did a qualitative evaluation of these, of the centroid measure, but also of other measures, and we used them for looking at 816 different scatter plots. And we found by qualitatively inspecting how a human would judge them and how the metrics judge them, that in over half of the cases, or almost half of the cases, the measures actually failed to model the human perception. And if we just took the real data sets, so the scatter plot sample from real data, then almost in 70% of the cases, the measures had some sort of issue. So this is probably not the final answer. So based on that results, my colleague, Michael Aupetit, back then contacted me and said, hey, this is essentially a computer vision machine learning problem that you're doing here. Why are you just modeling everything by heuristics? So what do I mean by that? And for the ones that are doing computer vision research, please forgive me about my naive view of computer vision. But computer vision for me is essentially, there's cats and dogs, okay? So, and we have lots of cats and dogs, and we have labels for them. We throw them into our training process, and then we get a lovely machine learning model here, our robot again, that for some unseen image can help us to tell whether this is a cat or a dog, right? Essentially, this is also what we need for visualization. So we want to model how humans perceive abstract data visualization. So we have, say, lots of labeled data where we can say, here's something, a scatter plot that has separable classes, and here's one that has no separable classes. And then, like, we train the model, and ideally later on, we will plug in some data into some unseen data scatter plot here into our model, and the model behaves like the human and would say this is separable. So this is what we tried in our 2015 Eurovis paper, and we really simplified that problem as a start. So we gathered some large collection of ground truth data, really just with a binary judgment, separable or non-separable. Then we predicted those with different models. So in this case, the models are essentially just our measures that we were talking about. And then in the end, we could evaluate the quality of each of these models by comparing them, how well they would predict the human judgments. And then we could just pick the model that best predicts the human judgments. Okay, so this is an easy idea, and it's essentially just a binary classification problem. So as I said, this is machine learning 101. We can use classical machine learning ideas on how to evaluate it. For instance, like, bootstrapping and then using the area under the curve, which we did here. 50% essentially means the algorithm, the measure that we took, did some random guess. 100% would mean like it perfectly predicts the human label. So here we have like the measures. We identified some like 34 different measures that we could use. And here's this AUC bootstrap. And so it turns out that the best measure was indeed the centroid measure back then by Mike Sips. So there's two reasons or two things that we need to keep in mind. So first is we only took very clear-cut examples as our training and also as our test data. So that means like we only looked at clearly separable and clearly non-separable classes in scatter plots. In the meantime, we also did some research on like, things in between, and things become really messy, specifically, involving human factors like, priming effects, anchoring effects, all that sort of thing. But for those, a centroid measure works really well. The other thing to mention is that we're at an 82.5% average area under the curve measure. So there's still 20% room for improvements here. And so this is, of course, like, as good computer science, we took that as like a great motivation to write a follow-up paper. Now having this automatic way of evaluating these measures and not needing to going out to run user studies every time you do that, we just created like, 2002 new measures by systematically just looking at the space and exploring the space of how we can model points, colored points, essentially in a 2D space. So we defined 143 different proximity graphs. So there's like, things like a Delaunay graph, like a KNN graph, lots of fun mathematical stuff. And also purity functions. So how can we break down these neighborhood graphs to tell us a number about the separability in these classes? So we did that, and then we actually found out that almost 60% of our new measures were better than the best state-of-the-art centroid measures. So this were quite promising results. And the best measure, without like now really diving into mathematical definitions here, almost scored a 93% average AUC. The best measure was computationally very expensive. So usually we suggested like a simpler one, a KNN one, which had like 92.4% average AUC. Okay, so now, of course, you think, okay, this is like very theory heavy. And what are you doing? You're talking of points and scatter plots, blah, blah, blah. So scatter plots are, by the way, fantastic. I love to quote Ron Ransing here, who said, scatter plots are essentially the fruit flies of visualization research. They're complex enough that we can do something meaningful with them, but they're simple enough so we can still understand the world. So that's our fruit flies. But I think like this idea of modeling perception with machine learning is really something that can also impact real applications. So we already said, okay, we can, for instance, use those models that we're creating here to select good views in a scatter plot. Of course, if you have like a five-dimensional view, this is not meaningful. If you have 10 dimensions, it's already like, 45 views that you would generate. If you have 200 dimensional data, you almost would have like, 20,000 views. And then those sort of things, they become interesting. They can help you to rank these 20,000 views, for instance. However, like, you probably paid attention, said, hey, didn't we talk about dimensionality reduction before? Why would I look just at a scatter plot matrix? Yes, you can, in fact, also use these metrics in a dimensionality reduction framework, which we did here together with my colleague, Yunhai Wang. So we used these metrics that we generated as an optimization criteria in a linear dimensionality reduction framework. So we remember linear dimensionality reduction essentially just means how do we put a plane into our high dimensional space and how, like, to project the data points onto that plane. And this is what we did. And so this is a very similar idea to classical LDA, linear discriminant analysis. And we did also a study, and we found that actually with the new metrics, we would get closer or we would get better results in terms of human beings saying, like, those views are actually showing more separable clusters. Of course, we can also do other tasks in the tasks. Sorry. In the meantime, we also used it for scatter plots that had no colors. So like what we generally would call clumpiness. So do I see like, some clusters, some clumps forming here? You can run the same process. You gather some ground truth data from human beings, train a model, and then use it. And we again found that our methods would align better, for instance, as the methods that were previously proposed, such as like, the skagnostics measure of clumpiness. You also can use it, for instance, for the task of assigning colors to classes and scatter plots. You see, we're still with scatter plots here. So the idea here is that you want to assign colors to a scatter plot so you actually can differentiate the classes well. So here, for instance, there's like, we built this method and it gives you like a low rank. So here you would see, okay, these classes, they have all very, very similar colors. They were hard to distinguish. And here's something where we assign like a high rank. So the colors are assigned differently. And here we have the green, orange, and blue, which are like, they're overlapping, but they're easier to distinguish here. And finally, of course, we can also use that approach, of course, for other types of visual encoding. So this is a paper that we published last year's 2020 InfoVis, where we use this optimization-based approach to essentially order different streams in a stream graph in a way that makes it easier to perceive for humans. So like these are the previous methods, and this is basically the output from our method from this optimization algorithm. Okay, so machine learning based visualization design, is this like just like, some fun thing, or is this maybe even like a new paradigm for doing visualization research after all? I think the real answer is probably somewhere in between, but I think like, there's definitely a lot of things that are worthwhile to considering. And I think there's trends that are going on that allow for that sort of research in a way that has not been possible, say, some 10 years ago. Okay, so one is that really scalable data becomes available. So if you look around, there's not just like this one paper that I'm citing here, but that paper from Kai 2019 essentially provided 31 million data sets crawled from the web that could be used for that sort of approach that we're suggesting here. But at the same time, we have scalable methods, and I mean both scalable methods in terms of like gathering the human judgments. So most of our study nowadays are on mechanical Turk. You just get like, much more feedback and quicker feedback. There's new challenges in cleaning and working with that data. But for these, like what I would call lower levels perceptual tasks, like those studies work really well. Please keep in mind, if I say low level perceptual task, a real psychologist would hunt me down for that, because for them what we are doing in Vis is already like, everything is super high level. But also the methods in terms of machine learning. And here I think the machine learning, deep learning hype is definitely something positive. So there's like essentially new models coming out of that area every week, every month. And like, you can try new things and like get better results of what we're doing here. So, oh, sorry. This is just a comment from a previous talk. Okay, good. So let's come to the last part. Visualization and machine learning. So how can we bring those two things together? I think in some ways the holy grail, and that's what I outlined in the beginning, is not like, one will help the other and the other will help the first one, but it's really like, leveraging the benefits from combining those into visual interfaces or like, solutions for humans. So I still remember, so shortly before the pandemic, we had Jeff Hare over giving a presentation here in Stuttgart that like now feels ages ago, but I saw this nice quote from Michael Jordan on one of his slides, and it's actually Michael Jordan, the statistics professor, not the basketball player that you might also remember and associate with the name Michael Jordan. And so who said we need well thought out interactions of humans and computers to solve our most pressing problems. Why do I think this is so important? Of course, we all in our community are bought into this idea for a long time. But I think now people also outside the community, in this case, statisticians, say like, this is really something, it's not just like a button that we press and every problem will be solved. We need to have good solutions to combine the strength of humans and computers. So it's an HCI problem. It's a human data interaction, a human model interaction problem. And so essentially, this is what I felt like, most of the more applied work that I have been doing ever since I started in the area of data visualization is falling back to this idea of combining some sort of algorithmic analysis techniques with some sort of visual human-centered technique. So here's like, on the left, a picture from like, one of the early tools that we built at BMW. On the right, there's a tool that we built with Manuela Waldner recently, where we you would organize sort of documents, and then by organizing the documents you can learn in the background an active model classification model, and then propose if you think those two things are together, you probably also should consider that this document could also be. So it's really a human machine collaboration task that we're doing here. But I think there's also challenges, and this is the things that I want to talk last now in this talk for today. I think the first challenge is really solving these real problems. And this is, again, something that I've been thinking about a lot for the last 10 years. Or even longer, is let's not just solve some ivory tower abstract problems, but how can visualization, how can these human data interaction tools be used out there in the wild? So some of you might have seen this design static methodology paper that we wrote in 2012, where we say here is a way to work together with real people in the wild that have data and driving problems. And I think this is was a sort of successful approach to do that. However, what I want to stress here is it's not the only one. There's in fact other ways. So you don't necessarily need to start with people out there in the wild. You can also start with data. So you have some interesting data set and you want to still make some impact. And here's some paper from Michael Opperman, my previous master student, who's now doing his PhD with Tamara Mansner in Canada, where they say let's do data first visualization design study. So we start with the data and then we reach out to people. There's also, I think, something that we did recently, or over the last 5 years, is we start from the models. So here's a modeling problem. Here's a certain type of models, and then we try to tackle these problems and reach out to people that for instance, in natural language processing, working with these types of models. Essentially, I think still, for all of these, it's important to remember the original goal, which is problem first design study. So we, in some ways, go full circle here. So there is many problems out there that will benefit from a combined machine learning HCI, machine learning visualization approach. The important thing now, I think, is to think about what are these problems. And for me, I love visualization, but I think the problems itself, they're not naturally just a visualization problem. people, they're not coming and say, I have a visualization problem, unless you want to visually communicate your data from the first place. But if you think about the analytical exploratory task, it's more about a human data interaction, human model interaction problem in and of itself. There's like, some people they have some data and they want to understand their data. And this can even be like in a everyday task that does not need to be like, in a complex, like, biology or medicine setup. And here are a few examples just to stress that point that I want to make here. So here's one of the papers that I really like from Sedlmair Amershi from KITE 2012, where they essentially proposed a tool, like, a recommender system where you would like, select some friends from your Facebook friend list to organize a party. Well, it sounds very distant in those days, but like there were parties at some point in the world. And then like, the algorithm in the back would take these in an active learning manner and suggest, if you invite these people, you probably also should invite those friends of yours, so they're not angry. So it's a human model, human computer collaboration here that we're seeing. So another example that I have here is like from our own work, where we were thinking about how to change recommender system. You probably by now, everyone is using some sort of recommender system. I was really resistant, still like, doing vinyls for a long time. But now I'm also like, using one of these like, recommender systems. And you get music and like, and the algorithm basically says, this is what I recommend first, and you don't have even to interact. But for someone that loves music, I was always unsatisfied because there's no way, or like only very simple ways of how you can bring your human needs and human expertise into that. It's basically just like thumbs up or thumbs down or clicking next. And so what we did here is like we did an approach where you could interact with the keywords. So for instance, the genre of a musical song, and then you would like select, oh, this is pretty cool. And then you see like, which keywords which tags were associated with that song, and then you select some that you want to have more, and then you get like some new music. And in fact, so like back then we tested that system. I ended up, I think, buying like 5 or 10 new albums because I discovered all this great new death metal music that I was not aware of. Pretty cool. So why am I talking about these things? These are not visualization interfaces. So if we send papers like that to Vis, I think what happens is, this is not a visualization problem. But I think like we should not restrict ourselves to just thinking about like visualization is the only way to deal with human data interaction problems. I would really encourage you to think about like, the general idea of like, humans and data, humans and models, and how they can interact. And I think this is also a trend that we're seeing. So like here, I put the pictures of like, a complex tool like, Photoshop, like, hundreds of features. Those are really great. But if you look at the trend from the last 10, 20 years, it's going away from that. What we have here on our cell phones, this is like, super easy apps. They're really targeted hammers for some specific nails. And maybe also in our area of visualization and human data interaction, we should think more of that. Okay, challenge number 2, interaction as a first-class citizen. So it's still funny, like, it's reviewing season again. We have Eurovis papers, and like you review all your papers, and like, and everyone says like, we have so many like great interaction possibilities in our tools. And what we see is like linking and brushing. And of course, we also did that, right? We talked about linking and brushing before in our Vis Coder example. Linking brushing is great, but I think there must be so much more than just linking and brushing. So what do I mean by that? So I think there's a few really cool examples in our community, like semantic interaction by Alex Endert, but also like the IPCA by Remco Chang and colleagues, where you like, say, okay, like by moving around points, by stating hypotheses in my scatter plot directly, I can change this like, way of how the data is projected. So this is really cool stuff, but I think that we would need more of that to really like get to the interaction between humans and models. So we have been doing with Jürgen Bernhard a lot of research on like, interactive learning. So like we create labels, the machine suggests other labels, and like, how can we express that? But also, and I have not been talking about that for today for too long, or not at all, in fact. But I think for the last 2 years, we already started also, and other people started looking into like, how can we finally go just beyond like post-WIMP. So people like Petra Eisenberg 10 years ago, they did lots of stuff on interactive tables. Now we have like a virtual augmented reality. Here's an example I personally like from Steven Bergner, where they said like, hey, it's a multi-dimensional space. Why can't we use like a music mixing board to interact with all these parameters? I think there's lots of opportunities to be explored here. Okay, so the point now, of course, is when do we need a human in the loop? Because interaction is only needed if we really need a human in the loop. And here I love to go back to this diagram that we also proposed in this design study methodology paper. Maybe it's just useful for myself, but I like to really think about the problem space as in 2 dimensions. One is the information location, which we see down here, which means like, where is the data? Where is the information? Is everything externalized already into the computer? Or is like, there's some tacit knowledge that only is in the user's head? And the other the other axis is the task clarity. So how clear is our task? It's like, throwing a coin into a vending machine is something really clear, but solving the task of like, healing cancer is very complicated, and it's a fuzzy task, right? So this is the classical axis of task decomposition also in HCI. We now, of course, could reason with these 2 axes about when machine learning and when visualization or human in the loop approaches are better. So if you have all the data in the computer, all the information in the computer, and your task is crisp, then you probably don't need a human in the loop anymore. So this is the idea. Think of like, driving a car. The task is well specified. I want to get from A to B. Like, we have all sorts of rules, specifically in Germany. And we're on the good way of like, getting all the data into the computer. Then that we probably end up here. But my feeling is there's this huge space here of like where we need human in the loop solutions. And whenever we work on some of these problems, the tricky thing for us is that like a typical Vis contribution would help us to move towards like, externalizing more data and making the task clear. This is sometimes hard for us because like, in the end, it's easy to say, hey, we could have just written a machine learning algorithm to fully automatize that all the way along. The good news is, I think like with each of these visualization problems, we detect new problems, but it's really like, it's much more exploratory. This is a nice paper by Joe Wood and colleagues, where they said like, okay, like we move along this axis, but at the same time, like there's this 10 new questions coming in. The point I want to make here is, I think so far we're really making point contributions without really connecting that in that space. So I'm coming back also to a paper here that's also a little bit older on the science of interaction and the call for action to do that in visualization. So at the moment, it's really hard and rarely done to say, okay, here's a solution for, say, biologists, and here's a solution for automotive engineers. Usually, like, they might have exactly the same abstract problem, but we are not able to link those together. So I think there's much work needed to have like this abstraction layer where we can like, plug in these human in the loop problems. Okay, challenge number 3, scaling up our solutions. And again, here I'm talking as a Vis person. So if I look at the typical machine learning data size in their papers, they work with much bigger data, I would say, than the Vis papers, at least in the InfoVis and the VAST side, which I'm mostly aware of. And like, you remember those were terms that we used last decade to describe visualization research. At the same time, what is surprising is that the time requirements in visualization, I'd argue, are much more strict than the time requirements in machine learning. In machine learning, we essentially, we go off, we let the computer compute our models overnight, and then we're fine. In visualization, ideally, we want to have like, feedback in a few seconds, not to break with our analytical rate, and even in a few milliseconds if we want to have like interactive frame rates. Okay, so there's a surprisingly little research. There's some, like, LDEF is doing a great job. There's also a recent trend, which I think Mark also, I remember we had a paper on that, like the opening the black box, which really made me think about this entire issue. So we have algorithms, for instance, that like, they're just taking too long. So we want to provide some intermediate results, and we want to interact while the algorithm is running. And so the idea is really to do that progressively. And we know progressive approaches probably from JPEG. So like ages ago, we remember we would go to web page and then like, you know, the cat image would like progressively build up like that. And this is not really good because like here we can't see anything. Like now it works like that. So like, you know, instead of like, you know, showing the picture bit by bit, we progressively increase the resolution of the picture, which works much better. And I think like, you know, that's this really interesting idea. So we had a Dagstuhl seminar on that, and there's like first contributions coming out of that. For instance, like this progressive TSNE that you can use to use TSNE to much bigger data sets, and to do that in a fashion that you don't have to wait until everything is computed first. So a pretty cool and promising area. Okay, so we're running a little bit out of time. There's many other challenges, of course, like, you know, the design process. Just like whenever I see this picture of like, you know, what are the data skills of the skills of a data science person, like, you know, they have to be like, you know, basically learn everything, which is, I think, like not possible. Instead, we need collaboration. There's like, you know, the evaluation of these human model interaction, human data interaction systems, Belief workshop, Viva ML workshop, they're talking about those sort of challenges. But the point here is that like, it's not, I don't want to be complete, but I wanted to talk about 3 challenges that I thought are important. Okay, to conclude. So first, we talked about Vis for ML, and we specifically dived a little bit into this area of visual parameter space analysis, which you probably figured that I really like because we did work in. Same for machine learning for Vis. I do really think this is a very important area, and I'm happy that more and more people are actually going down that route now. And then finally, we concluded talking about the challenges that, or 3 challenges that might ahead in like actually combining visualization and machine learning into something like, you know, that really benefits many people. I'm actually optimistic. So if we now think about like, you know, the things that are going on, people build up new labs for human-centered data science, explainable AI, trust in AI. Many trends are pointing towards that, like, you know, the human factors are becoming more important in this area of like, you know, making data usable for people and useful. So in the end, this is the last slide that I have been using for a long time now. Why do I think this is so great? Machine learning and Vis. So we remember all, like, you know, ages ago, there were things like, you know, a microscope or a telescope, which helped us to see the world in a completely new view. So for me, this is what's happening now through visualization. Visualization and machine learning together, this combination gives us a new lens to look at the data, the oil or the soil of like, you know, what's making research and like, you know, science, society, and industry viable at those days. On that note, I want to say thank you to my team and also to the many collaborators, and of course also for your attention, and I'm happy to take any questions.
Thank you. Thank you for the cool talk. We have time for a couple of questions. Who wants to start? Just unmute yourself.
I can start. I maybe missed some part because I had to take a phone call regarding the machine learning design, the machine learning based visualization design. Where do you get the training data from?
So essentially, we run user studies. So the goal is to model human perception. So we can run a lab study. That's what we did in the beginning, or even like a coding study where we have some coders like coding large sets of scatter plots. Now we do most of the studies on Mechanical Turk. So we get labels. For instance, like let's assume this like simple example again. Let's jump to slide 20 maybe. Yes, this was about right. So we have these scatter plots here. Yeah, we can. Oh yeah, this is a good slide. So we have these scatter plots. Basically, we put them on Mechanical Turk, and then we would collect the data. And of course, like, you know, I make it sound easy, and it's easy if you have like clear-cut examples. Is this separable or not? So if you have more complex, like, patterns of like mixing data, it's more complicated. And we also had a paper on that with a colleague from RWTH Aachen, where we showed that, like, there's all sorts of, like, human biases at play, and, like, priming effects, anchoring effects, that sort of stuff. But essentially we get, like, the short answers, we get them from user studies.
Mm-hmm.
And that's why maybe ground truth is a bad name, but
yeah. But do you need a lot of training data? I mean, if machine learning technique decides which visualization type is best to gain most information from particular data types, that's probably very domain specific, and maybe doesn't work for every end user in the same way. Is this like a problem? Do you need a tremendous amount of training data to map this correctly?
So this is a very good question. So far, I'd say we're still doing research in the classical machine learning framework. So we know how to model things. So we do the feature selection in some ways by hand. So we're not in the area of, like, deep learning. Some people have looked into that, where you basically also have the machine doing, like, the feature selection, or even AutoML, where, like, the machine just does everything on their own. For those sort of frameworks, you need much, much more data, of course. So there have been, like, people thinking about how can we, like, synthesize data and all that sort of stuff. But I think we're not there yet where we talk about, like, millions or billions of data points. So I think, like, we're still, like, down, and we know exactly what we're doing and how we're modeling these phenomena. The cool thing about doing the traditional machine learning thing, I think, is that we also get some sort of understanding of, like, how human perception might work. So, like, do we as humans differentiate, say, like, clusters by, like, mostly their centroid, or is this, like, something we take shape more into account? We have features that we can model that, and then we can look at the importance of the features basically in our evaluation framework, right? So I think we're not there of, like, using really big data, but this is, like, the last slide that I made. I think, like, things are becoming more and more available. And like, people also think about, like, end-to-end models now, but much more on the like, like, where you don't have a human in the loop, you can just generate your ground truth data without, like, running user studies. The yes. Okay, I forgot the last point I wanted to say.
So if I understand right, this is not using neural networks or deep neural networks, but it's more like a rule-based recommender system.
Yes.
You define the rules.
Now I also remember the last point I wanted to make. So as you probably noticed, we are working with really specific tasks. So, like, you have a scatter plot and you want to model the separability of classes. We're not at the point where we say, like, the machine is now recommending a certain visualization, but there's actually people that are doing that. So I know Jeff Hare's group, for instance, and Dominic Moritz, for instance. There are people with, like, their Draco system, for instance. They try to do exactly that, but they come from a different angle. And instead of, like, collecting all sorts of human data, and this they do it at, like, more formal and different approach. The thing is also, and I think this is open research, do you really, like, if we're now selecting between visual encodings, do we really want to make that based on usage data from human users? This in some ways, like, comes back to the question, is this really the ground truth? So maybe, like, people always selecting, like, a bad visualization. Think of the example that I showed before of, like, in the user study, actually comparing adjacency matrices and node link diagrams from Jean Daniel, they found that adjacency matrices are actually better in almost all of the cases, but nobody is using them. So from a purely data-driven point of view, we never would use adjacency matrices, because everyone always selects, like, a node link diagram, right? Although it might not be the ideal choice. So I think this is a little bit tricky and needs a different approach here.
Yeah, but that's the holy grail question in machine learning anyway. Is the training data representative for a particular task? Yeah. So this is not only here, but everywhere, I guess.
Again, I think, like, to understand how representative and how good training data is, you need human data interaction, you need visualization, you need people to judge that, and you need to have like, people are also different. Not everyone is the same. There's experts, and there's different experts in different areas. And I think this is why I think like these like human in the loop interface. I feel like I'm preaching to the choir here, but you all probably agree that human in the loop approaches for like, you know, working with data are really essential. But I think these are all reasons, and maybe the stories are not as easy to tell as like self-driving cars, but without that, we will never get at like, you know, self-driving cars.
So do you think the human in the loop can be replaced at some point when the human was long enough in the loop to make recommendations that you can actually automate this completely?
Yes. So this is the this graphic here, essentially. I feel like, you know, if you take a very specific problem instance, let's assume like, you know, driving a car. Okay, so driving a car is at this point, let's say. And so like the task clarity is like, okay, it's actually, or let's say it's over here. The task is really clear. Like, you know, I have all my rules, I need to go left, but we don't have all the information available. We get more and more and more and more information. So we get over here. So this very specific task might be doable fully automatic. Of course, like driving a car is not an analytical task in that sense. But I think this is how, at least my worldview is in that sense, that we will be able to automatize more and more, but like at the same time, like if we automatize things, let's say like, you know, in fighting cancer, there will be things that we can automatize, but at the same time, there will be like new questions from like, you know, looking at the data, working with the data, that we again, like, you know, need to have like humans and machines. And the tricky thing is like, you know, I think at the moment, it's really hard to say, I have this sort of problem, and then go into the Vis literature and say like, this is sort of the solution for my human in the loop problem. And okay, so this is probably like going beyond, but the question that hunts me down is like, is visualization design really a wicked problem that we cannot really like, you know, make into an engineering framework? Or is it like, you know, really an engineering framework where in the end you have like well, here I think Austria and Germany, I can use the Bible for visualization, where we can actually like look up and like, if I have like this abstract problem, this and that visual encodings with this interaction technique would be a good starting point. And then you can, of course, like, you know, encode it into a recommender system.
Mm-hmm. Last question from my side. How comes your junior professorship is for VR and AR?
Okay, that's reality. There have been not a whole lot of visualization positions in Germany and Austria. As you probably know, talk to Mark, he can tell you that. Okay, so this is the practical side, but I actually started in the very beginning. I told you that like I started from HCI. So originally I think of myself still as an HCI person, and I have done some VR AR work ages ago. And then like, you know, I applied for this position, as you know, so I'm at Visus here. It's a really nice area for doing visualization research. And of course, the VR AR stuff, I'm doing lots of VR AR stuff now. I have not been talking about that today. But there's really cool intersections also between VR AR research and visualization, like immersive analytics, but also like, you know, situated visualization was also like, I'm working with Dieter Schmalstieg here in Austria that you probably know very well. Mark at least knows him very well. And so there's many fantastic areas. There's many things that can go wrong. I think like, you know, now we have like all these new VR devices. The solution is not just like to put all our visualizations into 3D and then into VR. We had papers on that showed that this is not a good idea. But I think this is the sort of the idea that or many of my research projects at the moment focus on these sort of topics. And every now and then, it's actually cool to do something new again. I also have to say that. But this
yes, it is. So, further questions? Maybe I can continue then. So I have so you already answered my first question about the Vis design and whether you can just do specific models, specific tasks, or task-specific models, or could also do multitask stuff. But one specific question was also about the Vis Coder project. So each point is a projection of the same data set, right? With different parameters or different method.
Yes.
How is the distance defined between the projections? So if you have projections that are rotated but are just the same, is that taken into account? How is that defined?
Yes, this is a very good question. Thank you, Mark. For the original version of the Vis Coder, we tested different types of distance metrics. So how we essentially ended up doing it in the end is like, we made it rotation invariant, and then we measured the distance between each single point in these plots. But this, of course, is an essential question, because what we want to have in the end is a perceptual measure. So those should be perceptually similar when they appear close together. So I think there is some uncertainty in our approach at the moment. This is not the perfect distance metric. And in fact, so this is something we also talked about, I think, in the discussion and limitation section, that we tried different distance metrics, but in some ways, this is going full circle to the other area of using machine learning for Vis, where we want to train perceptual models that, for instance, can tell us about the similarity. There has been some really interesting work by Enrico Bertini. You probably know that, where they actually, made this affinity diagram, and then they let people organize scatter plots based on the human similarity. So this, in some ways, is what we want to have here. For our purpose, I think it worked well enough, but that's also because we had a very small design space with these 4 or 5 dimensionality reduction methods, and also the design space of TSNE is also rather smooth, maybe with some smaller jumps, but yeah.
Okay, thank you. Further questions? I think we have time for 1 or 2 more. Don't be shy.
I have actually a question about the machine learning part again. You said that the user study was about classifying separate or completely separated or completely mixed data points, which seems quite restricting. And I wanted to ask if you think maybe to change, it would improve the task if you change it to not is it separable or non-separable, but rather if you compare 2 different visualizations and let the user choose which one looks better.
Yes. So thank you very much. This is also a very good question. So yes, of course, we did that. So in fact, we tried out different ways of how to put out the task to people on Mechanical Turk. So this original work was based on an expert coding study, where we actually assigned a number from 1 to 5 on how differentiable 2 clusters or 1 cluster is from the rest. This is what we did, and then we basically only took 4 and 5 and said those are separable ones, and we took 1 and 2 and said those are non-separable ones, and we threw away everything. We also had 2 coders, and whenever 2 coders would disagree, so one would say 4 and the other 2, we also threw away that class. So this is what I meant with we really simplified things here for the first approach. Ever since, we actually did different studies, and we did exactly what you said. So we said we did it more a just noticeable sort of different experience. So which of the 2 clusters is more separable, and then people would select. And so on Mechanical Turk, we also use many more people. So instead of just having 2 coders, we go for 10 or maybe even 15 coders per class. So class means very often we use a 1 versus all. So it's a scatter plot, and we really want to focus on one of these classes because that's the data we need. And then we get 10, and we let them rate. There's ranking based approaches. There's also just giving me just a slider or whatever. We tried out different approaches, but I think the ranking based approaches worked really well. And if you have many people, you can also get some insights on the uncertainty. So for some scatter plots, people really tend to agree that this is separable. For some others, they really tend to agree that it's non-separable. And then you also see things okay, here, so you can even put that into your models, predicting an uncertainty value. right? And the other thing that we also see in our data now is that you see the individual differences. So some people, they're always negative. I never see anything. And some people, they're always optimistic, like, I see separability all the time. And then you also see, like, you know, differences between experts where they say, like, yeah, okay, this is clearly separable. And, like, you know, perceptually, it's not separable. So you see all these interesting things. We had a study where we compare all these things. Unfortunately, the PhD student working on that, she got a really good offer from Amazon, and she's now working for Amazon. So we haven't had time to write up this paper. But this is, yeah, it's not trivial to do that in the right way. And, like, you know, we only did it for one type of task, one type of the visual encoding scatter plots in that case. But that really makes a difference in how you can model the data and how accurate your models are. But I think, like, important is in the end always, like, if you talk about human perception, you can be rather sure about the easy cases, but, like, if it's getting tricky, there is really a lot of uncertainty just stemming from the human nature of the task.
Mm-hmm. Speaking of Amazon and Mechanical Turk, so recently we made some bad experience with a Turk study, and I think so Connie can confirm that, I guess. And the problem was, if you have tasks that are like cognitive tasks where people really have to think, then the easy way out to get the, I don't know, $1 is to not think too hard, right? And then you get bad results. And checking for that is difficult, and I think sometimes, depending on the task, not even possible. What's your take on that and your experience?
Yes, I do agree. Is that related to the blog post that Alex wrote?
No.
Okay, that's a different one.
No.
I would generally agree. So I think Mechanical Turk works well if you have, that's what I called like low-level perceptual tasks. Again, I think it's not really low level if you talk to a psychologist, a perceptual psychologist, but for our purposes, like, you know, touching the class's separability, this is a task that takes them, like, you know, a few seconds. If we do higher level analytical or cognitive tasks, it's much harder. And we usually not do that on Mechanical Turk. We thought about doing that. There's apparently like this expert Mechanical Turk, so where you can basically say, like, okay, you need to have like a certain a degree of expertise in a certain area, and then you're only allowed to do that. But the problem that you said remains, right? You know, people are not there to, like, you know, give you the perfect data for your study, but people are essentially there to earn their money, and they don't get a whole lot of money. So there's also ethical concerns. And so there might be, like, you know, some smart things that you can do to, like, you know, but then you would need to pay them much more money. But then, like, if there's an easy way out, people still would do the easy way out, right? Like, it's fully understandable if I can earn, like, you know, 30 euros per hour versus, like, you know, 5 euros per hour. If I do like a good job, then, like, it's the opposite of what we want to have, right? So I do fully agree.
Yeah. All right. Thanks so much for taking the time. I think we could continue this discussion like for the rest of the day. But in the interest of time, I have to cut it here. So thanks again, Michael. We're going to have the next ICG Lab Talk series in March, because we're going to have the semester break. And in March, Günther Wallner will present. So he's going to be the new professor at our institute, working on game computing. And he's going to give the next talk. All right, enjoy your rest of the day, of the lockdown time, and we see each other hopefully soon. Thank you, Michael. Thanks everyone for joining.
Thank you.
It was really super interesting session.